So that's all just anatomy stuff. You know that already. We want to talk about how we make urine. And it turns out there are 3 different processes involved in the formation of urine. One of them is called glomerular filtration. The next one's called tubular reabsorption. And the third one's called tubular secretion. Right? So 3 different parts to making urine. Glomerular filtration, tubular reabsorption, tubular secretion. Let's look at glomerular filtration first. It's just what it sounds like. You are filtering the blood and forming a filtrate. Right? The filtrate will eventually become your urine. It occurs at a huge rate each day, 180 liters a day, which we're pretty much all metric ignorant, right? So what the heck is 180 liters a day? About 45 gallons a day. The big industrial drums that they carry on the back of trucks, anybody know the volume in those? They're 55 gallons. So I'm talking 45 gallons, so almost that big. That's how much filtrate you form each day. Amazing, right? That's a lot of filtrate. Now, clearly you don't urinate that much a day. You'd never get out of the bathroom, right? And there'd have to be a hose stuck in your mouth. But a huge amount of filtrate each day, right? 180 liters a day. So we want to know, how is it that we form that much filtrate? Why is it that we form that much filtrate? And much of that has to do with the way that this glomerulus is set up. So if we look closely at the glomerulus, we find that there are relatively large slits in those capillary beds. So pretty large holes there. Not large enough to let proteins through, but still pretty large holes. There's something else that happens here, and that is that the afferent arteriole is much larger than the efferent arteriole. So it wasn't just by chance that I showed the afferent arteriole being big and the efferent arteriole being small in my diagram. If you come in with a really big tube and you leave with a really small tube, what's going to happen to the pressure in between? Think about your faucet at home. You turn the water on, now let's put a nozzle on the end of it. What's going to happen to the pressure? It's going to go up, right? And so by having a large tube coming in and a small tube leaving, we have an increase in pressure. Kind of hard to read on my diagram. I should have chosen a different color there for my model of the glomerulus and Bowman's capsule. But really, here we go again with capillary membrane dynamics. Okay? Capillary membrane dynamics again. So if we look at the hydrostatic pressure that's in the afferent arteriole and glomerulus, we find that it's about 50 millimeters of mercury in there in that glomerulus. That's really high compared to what we were talking about before, right? So very high pressure, that 50 millimeters of mercury. The hydrostatic pressure in the Bowman's capsule that's going to push back is about 10 millimeters of mercury. So we've been down this path before. We know what to do, right? So we have a push that way of 50 and a push back of 10 for hydrostatic pressure. So our net hydrostatic pressure is 40 millimeters of mercury into Bowman's capsule, right? We subtract the hydrostatic pressure that's pushing back from the glomerular pressure. Well, let's look at osmotic pressures. We know we have to consider osmotic pressures. And so if we look at the colloid osmotic pressure in the glomerulus, it's about 30 millimeters of mercury. And the colloid osmotic pressure in the Bowman's capsule is essentially 0 because proteins, 1, don't come through, but if they do come through, they move out of there. That 30 millimeters of mercury colloid osmotic pressure is quite high, right? Compared to when we were doing our capillary membrane dynamics before. It's high because you're losing fluid, and what's going to be left behind are the proteins in a more concentrated state. Right? So we have 30 millimeters of mercury pulling back and none pulling that way. And so if we had a net hydrostatic of 40 and a net colloid osmotic pressure of 30, our net pressure is 10 millimeters of mercury. And which direction is the fluid moving? Not a hard question. To the right, right? So we have 50 pushing that way, 10 back, and 30 pulling this way, so 40 total this way, 50 pushing that way. So a net of 10 millimeters into Bowman's capsule. So it's not in balance. There's not a balance. Instead, it's an imbalance of 10 millimeters of mercury pushing fluid into Bowman's capsule, and you lose large amounts of fluid because of that. Right? So we get this really high hydrostatic pressure. How fast that occurs is something that we call the glomerular filtration rate. Okay? How fast that occurs is called the glomerular filtration rate. And that's an important measurement of kidney function, is how fast filtration is occurring. So when people have kidney problems, one of the things that will be tested oftentimes is something called the glomerular filtration rate. To do that, they need to be able to track the movement of something, right? They want to see how something is moving from the blood into the urine. And it turns out that a common substance that can be used is something called inulin. This is not a misspelling of insulin. Okay? This is a new word, inulin. It's a carbohydrate. And inulin, it has the ability to cross the glomerulus, but it's not acted on by the body, so it's not enzymatically broken down, it's not reabsorbed. So if it shows up in the blood, it'll simply show up in the urine. So the concept here is that we can inject a certain amount of inulin into the blood, check to see how fast it shows up in the urine, and we'll know the glomerular filtration rate. And so the way we do this is we figure out what's the urine volume per day or per hour, or let's say per day. We figure out what the concentration is of inulin in the urine, and then we divide that by the plasma concentration, and we can get the glomerular filtration rate. And I have some sample numbers here that we can use to get this to come out in our ballpark. So let me go to my sample numbers for us here. So let's assume that the person was forming 720 mils of urine per day, and that the concentration in the urine was 2 milligrams per milliliter. Right? So this is the urine, this is the urine concentration, and that the concentration in the plasma was 8 milligrams per liter. Let's take care of our units first to make sure that we've done this correctly. So our milligrams can cancel, our milliliters will cancel, and liters is in the denominator of the denominator, so we know our final units are going to be liters per day. Right? So we're good that way. So let's see if we can do this. So I'm going to do a little easy math. I'm going to cross out my 2, go down to 8, and make that a 4. And 4 goes into 720. What do you think? 180 times, right? So I made it come out just perfect in this case. Liters per day.
Gary, could you go over again what it is in the denominator? What is the 720 and what is the 2?
So 720 is the amount of urine formed in a day.
Okay.
The 2 milligrams per milliliter was the concentration of inulin. There's only one N in inulin. Sorry about that. That's the concentration of inulin in the urine, 2 milligrams per milliliter. And then the plasma concentration when we first injected into the body was 8 milligrams per liter. And so our final units come out liters per day. All right, so we can figure out the glomerular filtration rate for somebody that needs this, have this test and has possibly kidney failure. Right? We can get the glomerular filtration rate. All right, so we have this huge rate of filtration, 180 liters a day. We must reabsorb most of that, right? Or you would spend all your time in the restroom. So the next process is tubular reabsorption. The reabsorption of these substances, water certainly, but also nutrients that we need. Okay, so the way that this system works is we dump pretty much everything into the filtrate and then we pull back what we want, what's vitally necessary. What's going to be left behind will be waste products. So we're going to do tubular reabsorption. That's large quantities of water and nutrients are reabsorbed in tubules. It turns out about 87% of the filtrate is reabsorbed in the PCT and Henle's loop. Another 12% reabsorbed in the DCT and collecting duct. 87 plus 12 gets me to 99. So we're reabsorbing 99% of the fluid. Only 1% of that fluid then ends up being lost as urine each day. Okay, so we're going to reabsorb 99%. 1% will be lost as urine. If we look at how reabsorption occurs, one of the mechanisms for reabsorption is active transport. So the nephron has active transport systems and co-transport systems, right? So active transport, I mean also co-transport system, to actively reabsorb the substances that we need. So we dumped good and bad into the filtrate. We can reabsorb by active transport. Sodium chloride, potassium, calcium, glucose, amino acids, vitamins, right? So the things that dumped in there that were in our plasma that we need, we reabsorb them. Now where do they go when we reabsorb them? They're going to go into those peritubular capillaries. Right? So this diagram is trying to show this idea. So we're actively transporting these things out of the filtrate. And when they're actively transported out, they're going to end up going into the peritubular capillaries. And of course, then we'll have them back into the circulatory system. So we haven't lost them. The pumps, the active transport pumps, have a limit. They have a maximum ability to reabsorb substances. It's not endless. Their maximum ability to reabsorb is called the tubular maximum. And if you exceed that tubular maximum, then these solutes will start to show up in your urine. If you exceed that tubular maximum. So we learned when we talked about diabetes mellitus, that these people have glucose in their urine. We know that they have high blood glucose and that they have glucose in their urine. Why do they have glucose in their urine? They've exceeded their tubular maximum. So think about the little pumps working in there. They can only work so fast. And if you get the glucose levels high enough, it spills over, if you will, into the urine, right? So it shows up in the filtrate. We can't pull the glucose back fast enough, and they're going to end up with glucose in their urine. You can exceed your tubular maximum really easily for vitamins. Just take a multiple vitamin, and what happens to the color of your urine? Turns kind of yellow, or sometimes depends on what you've eaten. Orange too, because you've exceeded the tubular maximum for those vitamins, right? So if you get the levels high enough, the little pumps can only work so fast, and then you'll start to see these solids showing up in the urine. Well, if we actively transport these substances out of the nephron, water will follow by osmosis. Right? So water is going to follow by osmosis, following the solutes. And so this, again, this diagram trying to show this idea. You start reabsorbing all these substances, water will follow by osmosis. Right? So it's going to come back, and that's how we're going to get the water reabsorbed. The third way that substances are reabsorbed is by diffusion. So that if you pull water back and there are substances left in the filtrate that are at a higher concentration than found in the blood, then they will move by diffusion out of the filtrate into the peritubular capillaries, first into the tissues, but into the peritubular capillaries. One of those substances that does that happens to be urea. So we know that urea is a waste product, but if you think about this, so here we are going down the nephron. If you think about the urea concentration being the same as what's in the plasma at the start of the nephron, but then we start pulling water out, the urea concentration is going to increase, right? If you pull water out, urea concentration is going to go up. And as that urea concentration goes up, then it's going to begin to diffuse into the peritubular capillaries and be reabsorbed. So that even though urea is a waste product, you reabsorb urea back from the filtrate. When we think about how the nephron works, that it filters the blood and blood comes back clean from the kidneys, the reality is blood doesn't come back clean from the kidneys. It comes back cleaner than what it was, but not clean, right? So we just keep sending the blood there over and over and over again so that we can gradually get rid of the waste products like urea. So some substances are absorbed by diffusion. All right. The third process, tubular secretion. Okay? So we have glomerular filtration, tubular reabsorption, tubular secretion. There are a few substances that we want to be able to regulate and get rid of dependent upon their levels that aren't going to be taken care of by tubular reabsorption. So we call this process tubular secretion. It's going to occur in a distal convoluted tubule. And in this area, we can secrete certain substances out of the forming urine, out of the filtrate, back into the blood. And this diagram is trying to show you that these substances include things like hydrogen ion, potassium ion, and ammonia. They're not showing you the ammonia here. So we can secrete these substances, right? See, they're showing potassium or hydrogen going into the filtrate, from the blood into that filtrate. Ammonia can also be secreted. We need to be able to adjust the acid and base in the body, and one of the ways that we can do that is we can secrete hydrogen ion into the forming urine to get rid of it out of our blood, right? So we can secrete hydrogen ion. This diagram is a little confusing, but it's only trying to show you that sodium is exchanged for either hydrogen ion or potassium. We know it's exchanged for potassium, we've talked about that, but it can be exchanged for hydrogen ion as well. We need to adjust the potassium levels in the body, and so we can adjust those potassium levels by secreting them into the forming urine, from the blood into the forming filtrate in the distal convoluted tubule. The ammonia one is kind of a strange one. If your hydrogen ion levels start to get too concentrated in the urine, down to around a pH of 4, the hydrogen ion acid will start to destroy your nephron, right? It's too acidic for you. And so the body has a mechanism of secreting ammonia into the forming filtrate to buffer the hydrogen ion, so that if we can secrete ammonia into here, the ammonia can combine with hydrogen ion and it will form the ammonium ion. So we can buffer the hydrogen ion, stop it from being so acidic, and get rid of, in a sense, get rid of extra hydrogen ion by secreting ammonia. Okay, so this tubular secretion is a way to do final adjustments.
So would that make it ultimately like an NH4? That's ammonia?
Yeah, it becomes NH4+. So before I go on, let me use an analogy here that I like to use. It's a silly analogy, but it works for me. Before I got married, by the time I would get to the end of a semester, my house was a mess. My wife makes sure that doesn't happen anymore. But my house would be just a mess at the end. By this time in the semester, it would just be a disaster, right? I mean, I have papers grading, I would just, you know, so I just let everything go, say, hey, I'll get it later. So imagine at the end of the spring semester, I said, you know what, it's time to do a really thorough spring cleaning. So I take everything in the house and I move it out into the yard, except for the furniture, right? So the furniture stays in the house, but everything else in the house is going to go out into the yard. So good and bad, out into the yard, I get the house really, really clean. That is glomerular filtration. Good and bad go out. Okay? I now need to do tubular reabsorption. So I'm going to go around the yard and bring back all of the things that I want to keep. So the silverware, blankets, clothing, everything goes back in, nicely organized, just where it needs to go. Okay? So it's all now back in the house, the way it's supposed to be. What's left out in the yard now?
Junk.
Junk, right? Stuff to get rid of. Right? So I call up the local disposal company. I say, bring a big dumpster. I got a bunch of stuff I need to get rid of. We put it all in the dumpster. And I say, come pick it up tomorrow. They come pick it up. They're driving away. And I'm thinking, you know, I've just done such a great job of cleaning my house. I go inside, and just as I go inside, I look on the top shelf of something, and I see a few more things that I should have thrown away. As they're pulling away in the dumpster, I chase it down the street, grab those things, and throw them in as they're pulling away. Tubular secretion. Right? So the last few things as they're pulling away, we can get rid of tubular secretion, secreting into that distal convoluted tubule the things that we don't want, the potassium ion, hydrogen ion if necessary. Okay. Let's talk about the regulation of urine volume. So